Okay, this is a follow-up video to help you understand how you use the ratios of similar solids when you're solving problems. So, if you understand the basic concept, you can go ahead and try working through these problems and then check your answer. I'm going to talk you through them. In the first example, we're given a scale factor with the information the base edges are 4 inches and 6 inches in my similar pyramids. So I'm going to go ahead and write a little note over here that my scale factor measurement is 4 to 6. And while we're at it, we should probably go ahead and reduce that. That usually helps us out and just makes things simpler. So I'm going to go ahead and rewrite that as 2 to 3 for my scale factor measurement. If the volume of the smaller pyramid is 189 cubic inches, find the volume of the larger pyramid. So I'm trying to get to volume, so I'm automatically going to go ahead and jot down over here what my volume ratio would be if my scale factor is 2 to 3 and I know that they are similar to each other. So I'm remembering from the chart and the concept of similar solids that we're going to take our scale factor measurements and we're going to cube them. So my volume ratio is going to be 2 cubed, my pen doesn't want to write, 2 cubed to 3 cubed, and if we go ahead and get numbers for that, 2 times 2 times 2 is going to be 8, 3 cubed is 27. Okay, we're going to use this number in a second, or this ratio I should say. I just kind of like to do the preliminary work, and the other way you can do it is sort of set up the proportion and then fill it in. Okay, at this point I am ready to set up my proportion. I'm going to look at my given information. I know that the volume of the smaller pyramid is 189 cubic inches. So I've got a volume measurement here. And I'm looking for a volume of the larger pyramid. So I'm going to put a V, or you can use X for your unknown volume. And the key is that you put the ratio that you put on the other side has to be the ratio of volumes, not the ratio of areas, not the ratio of bases, and therefore my 8 and my 27 is going to fill in that other ratio. Okay, if you put 2 to 3 there, that's going to give you the wrong answer, even if you correctly solve the proportion. At this point, I'm going to fly through the rest of it because you guys know what you're doing. We're going to get 8V equal to 189 times 27. I'm coming out with 5,103 for that. Dividing by 8. Volume is going to be a decimal. You're going to think you're wrong. 637.875. And we're talking cubic inches. That would be my final answer. Okay, that's probably the easiest example. Let's walk through another one. There might be one more element of difficulty in this. We've got similar cones this time, and this time I'm telling you the volumes. So I'm going to go and just jot down my information, volume measurements. There they are, 128 pi. I'm not putting the units right now, to 250 pi. And we're eventually going to be talking about areas. I'm just kind of skimming the rest of the question. So I'm going to go ahead and simplify my ratio that I'm given. I know that I can cancel the pi's. If you want to rewrite it as a fraction, if that looks better to you, that's fine. And 128, 250 might reduce. If you want to try reducing those, start dividing. We can divide by 2, probably 4. I'm getting a ratio of 64 to 125 when I go ahead and reduce 128 and 250. So I'm going to keep that as my ratio of volumes. And maybe this time we want to kind of set up our proportions, see what information we have. We've got the smaller cone has a lateral area of 112 inches squared. So I'm going to go ahead and put 112 in one of my ratios. Again, that's an area measurement. You might want to make a little note to yourself if you like to jot down words next to this. Technical difficulties. Pause while I get my pen ready. Okay, that's supposed to be a 2. We're just going to go with it. 112 square inches for the lateral area of the smaller cone. I want to find the lateral area of the larger cone. I'm just using A for my variable. Use whatever letter you want. And I know now that I need a ratio over here, but my ratio needs to be the ratio of areas, since that's what I have on this side. I've got areas. So I'm going to need to fill that in with a ratio of areas. Currently, I only have the ratio of volumes. So I need to do a little bit of work. There's actually not a way to get directly from volume to area ratio. So I'm going to have to go back to my scale factor ratio, and that's what I'm going to do first. Then I'm going to go ahead and figure out my area ratio. So my thinking is, let's go first back to scale factor, and I'm going to do that by taking the cube root of 64 and the cube root of 125. So cube root of 64 and cube root of 125 is going to be my scale factor ratio. Recall that you get the cube root by going to the math button on the graphing calculators. It's the third button on the left-hand row of buttons, and it should be the fourth option there. A little 3 in front of your square root symbol gives you the cube root. So go ahead and do cube root of 64 and cube root of 125. And hopefully you're coming out with a ratio of 4 to 5. So that would be my scale factor measurement. And at this point I can sort of cross that out because that gives me 4 to 5 for my scale factor. So I've got my scale factor, but I really need my ratio of areas. So I'm going to take the 4 and the 5 and I'm going to square them. Ratio of areas should be 16 to 25. Bingo, that's what I needed. That's going to go over here. 16 and 25 is my ratio of areas for two similar solids that have a ratio of volumes 64 to 125. At this point, we are now into the solving stage, and all we need to do is cross multiply and divide. Again, easy part. 16a equal to 112 times 25, which is giving me 2,800. And I'm going to go ahead and divide by 16. My area is coming out to be 175 square inches. For my lateral area is what I was really solving for of the larger cone. Okay, slightly more complex than the first example. Big difference is that in this one we were given volumes. We had to go back to the scale factor before we could get the ratio of areas to then use in our proportion. Okay, I'm going to make one more video, and it's actually going to have two slightly harder problems, so feel free to watch that to help yourself out. Okay, this is going to be my third and final video for helping you to solve problems involving ratios of measurements with similar solids. We could have ratios of side lengths, we could have ratios of areas, ratios of volumes. So let's get started. In example 3, we've got similar triangular prisms, and I'm going to start the same way I started the other examples that I walked through in my second video by identifying which ratio am I given. And the given ratio here has to do with base areas. The key word is, of course, areas. So I'm going to start over here and just note that my ratio of areas is 45 to 20. And you're used to this. I like to reduce that if I can. 45 to 20 does reduce to, you can divide them both by 5, and we're going to get 9 to 4. So just to keep things neat, I'm going to go ahead and put that on the right hand side when I reduce that. Now, we're given the height of the larger prism is 9 feet. We need to find the volume of the smaller prism. And you're going to notice this one is actually a little bit more difficult because we're not given directly a volume, but yet we have to find a volume. So it does ask you to find the volume. I'm going to show you two ways to do this. The first way that I'm going to show you is, let's make our proportion having to do with volumes because we're asked to find the volume. So volume of the smaller prism is what I'm looking for. I'm going to use V for volume. And that means I must know the volume of the larger prism. Or be able to find the volume of the larger prism. So a little bit of scratch work that I'm going to do. Whoops. A little bit of scratch work that I'm going to do right now is I'm going to say, hey, can I actually figure out the volume of the larger prism based on the fact that the height is 9 feet? So recall our volume formula for a prism is capital B times H, where capital B is my base area. And if you read between the lines, we're actually given the base areas, and that was what I initially circled as the given ratio. So the base area of the larger one is going to have to be this larger number right here, 45, times the height, which is 9 feet. A little bit abstract because I don't have a picture going on here. But the base area is 45, the height is 9. So I actually do know that the volume of my larger prism is 405. When I multiply that out, I had to do the calculation there. 405 cubic feet. And that's what I'm going to put in my first ratio. 405 is my given, and I say given in quotes, my given volume of my larger prism. I'm looking for the volume of the smaller prism. Now, before I get carried away writing my proportion here, I've got to remember that this ratio, my second ratio, my proportion, is going to have to be a ratio of volumes. I don't have a ratio of volumes. I have a ratio of areas right here. So I need to convert that to be a ratio of volumes. So we can't go directly from area to volumes because we have to cube the scale factor. It's already squared right now. We can't go directly from squared to cubing it. If we square the 9 to 4, we're going to actually be doing the scale factor to the 4th power. So let's go backwards and let's figure out the scale factor by taking my 9 and 4, and I'm actually going to do the square root of 9 to the square root of 4, and of course the square root of 9 is 3, the square root of 4 is 2, and that's my scale factor, reduced scale factor ratio. But I don't want the scale factor ratio, I want the volume ratio. So now I'm going to go from there, and I am going to figure out the volume ratio by taking my 3 and 2, and I'm kind of writing my work on the left here, 3 and cubing it, and my 2 and cubing it, which is going to give me a reduced ratio of 3 times 3 times 3, 27, 2 times 2 times 2, to 8. So I finally have my volume ratio, started with area and got my volume ratio, but did it by going back to scale factor, then going to volume. That's the ratio that's going to get to go right here. And I'm now going to plug that in, 27 to 8. Now we're down to just the cross multiply and solve. And I'm just going to go ahead and tell you that your volume comes out to be 120 cubic feet. Go ahead and check if you want and do the cross multiplying right there. 120 cubic feet for your volume. If you like that way of doing it, you are fine to just stop right there. Go ahead and try the next example. I'm going to show you one more way to do it, and this is just, some people it makes more sense for them to do it this way. You were asked to find the volume of the smaller prism. So what I'm going to do is basically take what I did and sort of reverse the process. I actually calculated, if you go back to what I have in purple over here, I calculated the volume of the larger prism so that I could compare it to the volume of the smaller prism. So I'm going to reverse that. Instead of calculating the volume of the larger prism, I'm going to actually find the height of the smaller prism using my 9 as my height. So I'm going to make a proportion with heights instead of volumes. So I'm going to be looking for the height of the smaller prism, and I know the height of the larger prism is 9. That was given information in the problem. 9 feet. I'm looking for the height of the smaller. Now if I'm comparing heights, I'm going to have to use my scale factor ratio, and my ratio over here is therefore going to be 3 to 2. We're solving a totally different proportion. We're solving for height this time. Cross multiply 3h equals 18. The height is going to come out to 6 feet. Now, how do I use that to answer the question? The question asks, what's the volume of the smaller prism? Volume of the smaller prism is base area times height. Base area of the smaller prism is 20 square feet. That was in the problem. 20 times my height of 6 is going to give me a volume of 120 cubic feet. And indeed, that was exactly what we got when we solved it the other way. Difference is that I did that by having to do a calculation at the end. Here I did the proportion at the end. Two equally good ways of solving it. Pick which one makes more sense to you. And let's try the fourth one. So looking at one more. Yeah, you're going to have a couple parts to this. Let's walk through it. So we've got spheres this time. Have volumes in the ratio 8 to 343. And we want to find the surface area of the larger sphere. So I'm going to start by sort of mapping out my information, writing down what I have. I've got a volume ratio, 8 to 343. I don't believe that that can be reduced at all. That's always my first thought, is can I reduce that? So I'm going to keep that at 8 to 343. And I like to set up my proportion. Note what I'm solving for. We're trying to find the surface area of the larger sphere. So I'm looking for an area. That means I must know an area or be able to find an area. It doesn't look like I'm given an area, so I'm going to have to calculate a surface area for my smaller sphere. So let's look at the other information. We're given the diameter of the smaller sphere is 12 inches. So surface area I know to be 4 pi radius squared for a sphere, which is going to be, in this case, 4 pi times, don't forget to take the diameter and divide it by 2, 6 squared. 36 times 4 is giving me 144 pi for my surface area of my smaller sphere. That's my one ratio. Now I'm going to try to get my second ratio. It's going to have to be ratios of areas. So I'm looking for my middle row here, but I can't go directly from volume to areas. I got to go back to scale factor. So I'm going to go back to scale factor by means of taking this and taking the cube root of 8, comparing that to the cube root of 343. Again, in your calculator, go to the math button, the third one on the left-hand row of buttons there, and it should be the fourth option there for you to do the cube root. Cube root of 8 to cube root of 343, that simplifies to 2 to 7. And then I'm going to take that answer, and now I'm going to go here, and I'm going to take my 2, and I'm going to square it, and I'm going to take my 7 and square it, and I'm going to get 4 to 49. So I've got my three ratios here. I'm choosing to use this one because it's my ratio of areas. That's going to go right here, 4 and 49, and you're cross multiplying and solving. Area should come out to be 1,764 pi square inches. Okay, so cross multiply and divide. Make sure you can get that number, but again, that's the easiest step on these, is to go ahead and solve the proportion. So one way to do it, I will briefly kind of touch on the other way to do it. Follow my third example, and again, we're going to reverse the proportion and the solving. So in this case, I could have done a ratio of diameters because I know that the diameter of my smaller sphere is 12. You're looking for the diameter of the larger one, and we could have used the ratio or the scale factor of the side lengths. Diameter is a scale factor measurement in my proportion. So that would have given me, cross multiplying, 2D equals 7 times 12, which is 84. Dividing, I would have gotten a diameter measurement of 21, of course, inches. And from here, then I would have gone ahead and done my surface area calculation. We know surface area is 4 pi times my radius squared. 4 pi times diameter is 21, so we'd have 10.5 squared. And it looks like I made a brief mistake. I apologize. On my note sheet, I had done a radius measurement here. You could have done diameter measurement, but my calculations that I was using, for my paper were 6 was my given radius, and I was solving for my radius. So again, you could have done the diameter, but this should have been a radius measurement. Eraser. Radius of 21 inches. So let's correct that, and plugging in here, you should have a 21. 21 squared times 4 gives me 1,764 pi. There we go. Now we're getting the same measurements as what we got up here, because again, I'm calculating surface area. Same thing I calculated there. Just two different ways of doing it. So you pick which one makes more sense to you, but you got to make sure that whatever ratio you have on the right is matching up with the measurement you're solving for, whether it's a scale factor measurement, an area measurement, or a volume measurement. Hope those examples help. Good luck with the ones you try on your own.